Okay, today we're looking at second derivatives. Now this was studied a little bit in year 12, but I want to kind of go into a bit more detail in year 13. So say we've got y is some function of x, we're just looking at explicit definitions for second derivatives. Then what we can do is we can apply the differential operator to both sides of the equation, and we end up with dy by dx is equal to f primed of x. And what this represents is the rate of change of the function. Let me say the rate of change of f, or you might know it as the gradient function. But if we apply the differential operator a second time, we end up with what we call the second derivative. And we pronounce it d2y dx squared. So that's d with a superscript 2, y dx squared. And we can then notate that as f double primed of x. And this is sometimes referred to as the double derivative. Or the rate of change of f primed of x. So it looks at not how the function is changing, but how the gradient of the function is changing. Is the gradient increasing, or is the gradient decreasing, or is the gradient staying the same? Okay, so that's what second derivatives are. What do we do with them? Well, what I've got here is I've got a table, and across the top I've got different sets of y primed values, and then across the left I've got different sets of y double primed values. So what we're going to look at here in these columns are the values of the gradient, and what we're going to look at in the rows is the values of the second derivative, and we'll have a look at what this means graphically. So let's start in the top left. We've got a positive gradient, which means the curve is moving from down low to up high. But because the second derivative is positive, that means not only is the gradient positive, but the gradient is increasing. So the rate of change of the gradient is positive. So the gradient is getting steeper, it's getting more positive. So it is positive to start with, but it's getting more positive. So it's increasing. Okay, the gradient is increasing. Whereas down in this quadrant, this area, this ninth of the graph, we're going to have a positive gradient still. So it's going to still go from a low point to a high point, but the gradient is decreasing because the rate of change of the gradient is negative. So we've got a positive gradient, but the gradient itself is decreasing, so it's getting less positive. So it starts off quite positive, but it's getting less positive. It is still positive, but it is less positive. The gradient has decreased. Okay. And then in this quadrant, section up here, we've got a negative gradient, but the gradient is increasing, so it is quite negative to start with, and less negative to finish. Okay, it's negative all the way, but because the gradient is increasing, it's going from a higher negative value to a lower negative value. For example, it might go from -5 to -2. The gradient has increased, but it is still negative. And down in this section, we've got a negative gradient and the gradient is decreasing. So we have something that looks like this. Okay, the gradient is negative all the way through, but the gradient is getting more negative as x increases. So the gradient might start at like minus half maybe, and then as you increase x, it's getting more negative. So the gradient is decreasing. Okay, so that's what those four sections look like. Now, down here, we know that when the derivative is 0, we have a stationary point. But we use the second derivative to decide if it's a minimum or a maximum. So we've got a stationary point, so we're just looking at a single point now on the curve, but the gradient is increasing. So if the gradient is increasing at the point when the gradient is 0, it has to have gone from a negative gradient to a positive gradient. That's the only way it's going to happen. So that's why we can use the second derivative to decide if it's a minimum. So at this point here, just at that point, y primed is 0 and y double primed is positive. Okay, that's why it creates a minimum. And similarly down here, the gradient is decreasing. The only way that's going to happen is if it's gone from a positive gradient to a negative gradient. That's the only way a gradient can be 0 and decreasing. At this point here, the gradient is 0, so y primed is 0, and y double primed is negative. Okay, that's all year 12 stuff really, or these two are year 12 stuff. Year 13 stuff, we look more at this row. What happens here when the gradient is negative but the second derivative is 0, or when the gradient is positive but the second derivative is 0. Okay, so let's look first of all here. The gradient is positive, it must go from a low to a high, but we could have gone from an increasing gradient to a decreasing gradient, or we might have gone from a decreasing gradient to an increasing gradient. We're assuming y is continuous, so it has to have gone from either here to here or from here to here, or it might have gone from here, there and up, or from here to 0 and then back up again, but we'll look at that case in a minute. Assuming it's continuous and it doesn't kind of go back on itself, it has to go from negative to positive or it has to go from positive to negative. So that means it's either going to go like so the gradient was decreasing and then at this point here it starts to increase again, or it was increasing and then at some point it starts to decrease. But along the whole of that curve, or both of these curves, the gradient is positive. So at this point here, y primed is positive and y double primed is 0. And at this point here, y primed is positive and y double primed is 0. We can do the same thing over here with the negatives. So it could go from a negative increasing to a negative decreasing, or it could go from a negative decreasing to a negative increasing. But at both of these points, here and here, the gradient is negative, so y primed is less than 0, but y double primed is 0 at both of these points. Because the gradient is neither increasing nor decreasing at those points. The gradient of the gradient is stationary, is 0. Okay, right, so let's put some names to some of these. We know that when dy by dx is positive, then this is an increasing function. That's something that was looked at in year 12. We know that when dy by dx was negative, it is a decreasing function. And we know that when dy by dx was 0, then that is a stationary point. Okay. So that's always true. When dy by dx is 0, it is a stationary point, guaranteed. It could be a minimum, it could be a maximum, and it could be one of these. We'll come back to that section in a second. Okay, what about the rows? Well, if this is true, the second derivative is positive, then we refer to the curve as being convex. Convex. Okay, convexity. So if a question is asking about a curve being convex, then you need to make the link that that is the second derivative is positive. And similarly, if it is negative, then we need to make the link that it is concave. So talk about concave function, that means the second derivative is negative. And the way I remember that is if its second derivative is negative, you end up with a shape that looks like this at a turning point. That kind of looks like a cave. Okay, so that's just the way I remember it. But there are many other ways, I'm sure you can remember it. And usually, I'm going to put usually here in brackets, these are called points of inflection. So point of inflection. It's not always the case. This is the only one that's not always true. If the second derivative is 0 and the first derivative is non-zero, then yes, that is always true. It is always called a point of inflection. But if both of them are 0, then we don't know what happens here. this could be one of three things. It could be a minimum, it could be a maximum, or it could be a stationary point of inflection. You just don't know. It's one of those three, definitely. Well, it might be a negative stationary point of inflection. So it's one of these three. It's either a local minimum, a local maximum, or a stationary point of inflection, but we don't know. The point is it's not always a point of inflection when the second derivative is 0, because it could be a local minimum or it could be a local maximum. Okay, so just be careful with that. These points are called points of inflection. They're not stationary points of inflection because the gradient is not 0 at those points, but we still refer to them as points of inflection. A stationary point of inflection is one like this, where the gradient goes from decreasing to increasing or increasing to decreasing, and the gradient is 0 at that point. Okay, so it satisfies both the criteria for point of inflection and stationary point. We refer to that as a stationary point of inflection. So what you can do to decide if it's a minimum, a maximum, or a stationary point of inflection is you can either use more derivatives, and there are rules which you can follow to decide. You can follow flow diagrams, for example, to look at third, fourth, fifth, sixth derivatives, etc. And that can allow you to analytically decide if it's a min, max, or a stationary point of inflection. For the A-level course, you're not expected to go past the second derivative, so we tend to use something called gradient profiling. And that will allow you to decide if it's a min, a max, or a stationary point of inflection. And that's essentially looking at the gradient to the left, the gradient to the right, and then deciding if it's positive 0, negative, then it's a max, negative 0, positive, then it's a min, positive 0, positive, or negative 0, negative, then it's a point of inflection. Okay, that's essentially what gradient profiling does. Okay, so I quite like this table. It allows us to see all of the possibilities at once, and if you're in this middle section here, they're both 0. We need to do further analysis to decide what is actually going on there. Okay, let's have a look at some curves. Let's just see what the second derivative looks like. So let's look at the first derivative first of all. We've got this point here is interesting, this point here is interesting. To the left of that, we say it's an increasing function because the gradient is positive. Okay, so y primed is greater than 0. Between these 2 points, we say it's a decreasing function. That is, the gradient is negative because it's going down. And then to the right, we say it's an increasing function again, because y primed is positive, the gradient is positive. Okay. At those 2 points, y primed is 0, which is why I've put hollow in there, because it's not included in these ranges. So at this point, y primed is 0, and at this point, y primed is 0. So it's gone from a positive gradient to a 0 gradient at that point, to a negative gradient, to a 0 gradient again at that point, and then to a positive gradient again. That's the first derivative. The second derivative, the point of interest, is here. This is called the point of inflection. So at that point, y double primed is 0, and the curve has moved from a concave state, which is the first bit, to a convex state. That's the second part. So over here, we refer to this as concave, and that is because y double primed is negative. Okay, the gradient is decreasing, it's quite positive, it's less positive, it's 0, it's negative, it's as negative as it gets. Okay, so therefore that is decreasing all the way around. And then to the right of that point, it is convex. That is, y double primed is positive. Okay, and that's because the gradient is moving from its most negative point to a 0, and then it's increasing past that. So the gradient is getting more positive. The gradient is increasing. The gradient is increasing. So the gradient of the gradient is positive. And this point here is referred to as the point of inflection. This is a stationary point and this is a stationary point. Okay. And this one here, again, we can have a look at all of this. This is going to be a stationary point, but it is increasing on both sides. Okay, the gradient doesn't get negative at any point. The gradient is 0 at that point, but to the left of that point, it is an increasing function. That is, the gradient is positive, and to the right of that point, it is also an increasing function. So y primed again is positive. Now at this point as well, we have y double primed is 0, and that has moved from, you can see the gradient here is decreasing until it gets to 0, and then the gradient starts to increase again. So to the left, because the gradient is decreasing, that is a concave part of the curve, which means y double primed is negative, and to the right, that is a convex part of the curve, y double primed is positive. And at that point, y double primed is 0. So at this point, y primed and y double primed are both 0. So if you just had that analysis, you wouldn't know if that's a minimum, a maximum, or a point of inflection. But we can see from the graph that this is, in this case, a stationary point of inflection, because the gradient is 0, the second derivative is 0, but at that point the gradient is positive on both sides. So because the gradient is positive here, then 0, and then positive, that fits the definition of a stationary point of inflection. Okay, 2 example questions before I finish up. Find the coordinates of the points of inflection of the curve y equals e to the minus x squared. So points of inflection, then we're going to need to set the second derivative to be 0, and we need to check, so also check that y primed doesn't equal 0 at that point. Okay, because if it doesn't, then we know it's a point of inflection. If it does, you need to check to make sure that it is a point of inflection. So let's answer this question. We need this first derivative. It's going to bomb through the derivatives. If you're unsure of how to differentiate these, check out previous videos. So it's going to be minus 2x times e to the minus x squared by the chain rule. And then y double primed, we're going to use the product rule. So we're going to do this times the differential of that, which is going to be 4x squared e to the minus x squared, plus that times the differential of that, which is minus 2e to the minus x squared. And then we can factorize that. So that's going to be 2 into 2x squared minus 1 e to the minus x squared. So that's the second derivative. We want a point of inflection, so we're going to set that to be 0. That can never be 0 because it's an exponential. 2 is never 0, so that implies that 2x squared minus 1 must be 0. And if I add 1, divide by 2, and then square root, I get x then must be plus or minus root 2 on 2, or 1 on root 2, the square root of a half. Okay, lovely. So those are the x coordinates. Plug those into here just to check that y primed is not 0 at those points. So y primed when x equals root 2 on 2 is equal to minus root 2 times e to the minus a half, which is not 0. I don't actually care what it is. I just know that it's not 0. So therefore that is a point of inflection. And y primed when x is negative root 2 on 2, that's going to be positive root 2 e to the minus a half, which again is not 0. Therefore that is also a point of inflection. So they're both points of inflection in this case. Great. So I've got the x coordinates. I now need to find the y coordinates because it's asked for the coordinates. So I need y values. So y when x equals root 2 on 2. I'm going to plug that into y now. So that is going to be e to the minus a half. And y when x is minus root 2 on 2 is also e to the minus a half, because the function is actually an even function. So that tells me that the coordinates are root 2 on 2 e to the minus a half. And this bottom one tells me negative root 2 on 2 e to the minus a half as well. And those are my 2 coordinates of my 2 points of inflection. Great. Second example, just to finish up the video. Here we go. F of x is x to the 4 times cosine of x. Find f double prime of 0. So answer to part A. We're going to differentiate twice. So f primed of x is going to be this times the differential of that, which is 4x cubed times the cosine of x, plus that times the differential of this, which is minus x to the 4 times sine of x. Okay, we are in radians. And then f double primed, going at this times the differential of this, which is 12x squared times the cosine of x. Okay, it's another product. So it's going to be that times the differential of this, which is minus 4x cubed times sine of x. Then over on this one, we've got that times the differential of this, which is the same as that actually, so we're going to times that by 2. And then that times the differential of this, which is going to be minus x to the 4 times the cosine of x, which I can then simplify a little bit as x squared into 12 minus x squared times the cosine of x minus 8x cubed times the sine of x. Okay, so there's my second derivative. The question's asked for f double primed of 0, so let's plug 0 into that. So f double primed of 0 is 0 minus 0, which is 0. Okay, brilliant. F double primed of 0 is 0. Part B. Decide if 0, 0 is a point of inflection or not on the curve. Justify your answer. Okay, so we've already decided that f double primed is 0, so it might be a point of inflection. What we need to do is just test the first derivative. So if I type in f primed of 0 and just check if that is 0 or not, I'm going to get 0, okay, 4 0 cubed minus cos 0, minus 0 to the 4 times sine of 0, that's also 0, so that's 0. Okay, well it still might be a point of inflection, because it might be a stationary point of inflection. So what we need to do to answer this is we need to gradient profile. Okay, so we gradient profile. You can use higher derivatives and still get full credit, but on this course you're not expected to. So what I'm going to do is I'm going to calculate y prime, the gradient, for different x values. So the middle x value is going to be the x value in question, which is 0, and then I want to move a little bit to the left and a little bit to the right of that to decide if it's positive or negative either side of my stationary point. So I'm going to do minus 0.1, and I'm going to do 0.1, and I know the gradient at this point is 0. So best way to do this is to jump into table mode. So if I jump into table mode, type in my function, which is 4x cubed times cosine of x minus x to the power 4 times the sine of x, and I want to set it between minus 0.1 to 0.1, and I'll go in steps of 0.1, could go in steps of 0.2, but it doesn't matter. Right, there we go. We can see that at this point it is minus 0.004, and at this point here it is 0.004. So the gradient has gone from a negative gradient to a positive gradient at this point. So to the left of the stationary point, the gradient is negative. At the stationary point, the gradient is 0. And then to the right of the stationary point, the gradient is positive. So that is not a point of inflection. That is a local minimum. Okay. So therefore we can conclude 0, 0 is not a point of inflection. So it's one of those cases where although the second derivative is 0, it doesn't mean that it is a point of inflection. Okay, there we go. All right, thank you for watching.